All right, so good morning. So let's start with the final, the last lecture of this course. Okay. And please feel free to ask me any doubt, anything that you have, or you can reach me even later if you want. Okay. All right. So we have used many books for the course. Of course, some nice books. They are very good books, in this topic, in this subject. Like Three Pieces book is quite nice, based on Linux. Then we have also used Anderson and Dahlian's book. That's used in many universities in US. The classical books are the two, Silversarts and Galvin, and the Tannenbaum. Apart from that, we have used a book by Robert Love. This is the main book on Linux. Okay, there, of course, he has written many books, and all are really good. And also we have used a book by Mark J. Rochkind or something like that. Okay, so these were the main books, and also we have used the base of the course, the basically flow of the course came from CS162, that's University of California, Berkeley. Okay, so that was the base that I have taken, and then used various books and resources to build up the course. Okay, we have covered the following topics. We started with basic OS introduction. What is an OS? And then we looked at the OS concepts, like it provides abstraction, OS requirement, runtime image, and all that. Then we studied threads and processes. Then we looked at dual mode of operation. Then within a process, where process states are stored, like concept of PCB, process control block. Then we have also studied system calls, essentially how a process can interact with OS. Actually, if certain things a process wants to do, it has to take help of OS, and OS can do these tasks on behalf of process. And because process cannot access certain memory arrays, so we have system calls. Then we have looked at the inter-process communication, then process synchronization, scheduling algorithms, deadlocks, what is a file and file systems, then IO device and device driver concept. We have also studied something that we couldn't cover in last course, that is computer architecture, but that's about disk and SSD. Then we again came back to file system design. And at the end, we have studied data center cloud at very abstract level, and then distributed systems. So that these are the major topics that we have covered. Okay, so we started with this. Okay, and something this we have covered earlier in computer architecture course. We have in our architecture course, we looked at what goes inside a computer, right? Primarily focus on the hardware. Okay, we there we have seen that this concept of processor or ALU connected to memory, and then there's a control unit and IO unit, right? So these are the four elements, and then we have gone in detail about all these concepts in earlier course. Okay, so that was at the hardware level, but the hardware cannot be presented to a user, because user doesn't want to get into details of what the hardware is inside. What is the depth of pipeline, how many pipelines are there, and all these things. User, even if there is a single user, no security issues, even then it will be major headache for user to run a program on their hardware. Okay, so now it means that now there is a need for a software, okay, that runs on top of all this hardware, right, and abstracts away or hides all the details of hardware for many reasons. One, of course, is the convenience to user, or the virtual interfaces provided to users, so that user just takes care of or does the job that user is supposed to do, the programming or execution of the program. Okay, and all these things, how resources are managed inside, how resources are provided to user, how resources are shared among user, how to provide security, and all these are the task of then OS, right? So the OS provides here an abstraction or interface to program. So these are the applications or programs that run, and they have to go through OS to use hardware. Okay, so that's the basic concept, right? All right, and this is, so basically OS provides a virtual world, okay, to users, right? And this what there are, or OS provides abstraction to user, and there are various ways of providing abstraction, right? So first important abstraction that we have seen was process or thread. Okay, so if so process or thread gives abstraction of a processor. Okay, so a user may not know anything about the processor, right? But the user program will do computation, and this computation is, done by the process, right? So user knows only about the process or thread. Okay, there's a one major abstraction. Okay, so user may think there are multiple processor inside corresponding to multiple processes. Okay, there's a visualization, right? If you write 5 programs and then execute all 5 together, I mean, you may think that there are 5 different processors available. Okay, you need not to know about multi-programming and all that. Okay, so there's a level of abstraction provided. Like, I mean, for example, till the beginning, of course, many of us were thinking that OS runs all the time on a system, right? In a single CPU, then we know that only one thing can run at a time, either user program or OS, but that's abstraction that we have, that OS runs all the time because it's available to us whenever we want. Okay, that was one. So thread and process is one major abstraction. Second was address space. Okay, address space is just a beauty, right? Our say physical memory is limited, and if number of programs are running on that corresponding to different user, then user need not worry about where to run the program, what part of the memory, which part of memory is free, and all that, those things, right? So now this concept is there that each program can use or each process can use an address space. Okay, which is this address space is starts from 0 up to 2 raised power whatever is the size of register or program count, right? Okay, so for 32-bit machine is 0 to 2 raised power 32 minus 1. So that each process can think that the whole this address space available. And this is such a beautiful concept. Then when you write a program, you never bother about all these details, right? What should be length of program and all that. Okay, so now okay, but this translation, because abstractions have got to be implemented, and this translation is done by what we have seen is memory management concept, right? Virtual memory concept, etc. Okay, using paging or segmentation or something else. Okay, all right. So, and third concept that we have is that of file. So program can execute and die, thread can execute and die, but certain things, the information that is generated or used, that if that is to be retained, then it has to be in the secondary memory. And secondary memory, then we have to give structure, how information is to be stored, and that's called file. It's nothing but named object, right? And it's such a lovely concept that everything, including OS, when it is when machine is about to start, is there in the file. Okay, so everything when your program is your machine is sleeping, okay, or off, is there in the file, and everything is pulled out from there, right, when it starts up. So it's a beautiful concept. And then we have also seen how files can abstract. The file concept also gives abstraction for IO. Okay, all the operation that we do for IO, for example, can be mapped to file operation, reading, writing, and others. Reading, writing, or whatever, initializing, or many operations. So that's the third important abstraction that we have seen. And then of course we can further go up to level of program, and then we have seen that we have concept of sockets. Now these sockets need not to be these sockets can be anywhere, right? A socket in one machine which is in your lab, and other machine could be a lab in Berkeley. Okay, so the socket programming gives you absolute higher level abstraction, and we have seen that socket is nothing but sockets are provided with a combination of IP address and port number. Okay, all right. So this is what we have seen in the course. Okay, and then we have seen the concept of system calls and system libraries. Okay. All right, so this all we have studied, and then we have studied the concept of IO. So other thing that OS does is background management, like for example, power management or network management, and all the operations inside, garbage collection or cleaning up, allocation of memory, for example, allocation of RAM or management of hard disk, and so on. A lot of things are done by OS in background. Okay. Okay, so address space concept we have spent significant time both in architecture course and in OS course, but just to reiterate, so we write program in higher level language, and then using compiler, assembler, and linker loader, etc. linker, we create a.out. Now here is shown a single step to reach to executable, but consists of multiple steps, and you will learn all about it when you study compiler course, right? Okay, and when this executable is available to us, okay, now note that executable is a file, okay, and it's in hard disk or flash, whatever, secondary memory. Okay, and then this executable, a file has to be brought into main memory for execution, then it becomes process. Okay, or we call it process image. Okay, and that's what it is. This is a process image. Of course, address space will include part of OS. Okay, so and in this process image we have seen we have a program part. Okay, where program instructions are there. Of course, is in machine language. Then data part. These are nothing but global data or static data. Then heap and stack. So this we have studied in detail, and then within stack we have frames. Okay. All right. So this concept we have studied. All right, and then this is how when we execute a program, and all this is brought into the memory. That's okay, and then the program counter will point to the instruction in this process image. Okay, and then stack pointer will point to the stack. So simple, right? And this all we have studied in detail, right? Each process will have its own address space and process image. Okay, we note that a program becomes process when it is brought for execution in the system or main memory. Okay, all right. And then we have seen that your program executes in virtual address space, and then there's a need for a translator for conversion into actual physical address space, right? So when you have you write a program and then it's compiled, it's in a machine instruction. Okay, then machine instruction, whatever addressing is there, okay, that is a virtual address. Okay, and then when its actual execution happens, then this is translated for instruction by instruction basis. And this concept we have studied in detail in computer architecture course, right? So this is the concept that uh, so this address space is used for execution, and then actual translation happens at runtime, and that we call and this translation can be through various mechanism, and the one which we have seen is using paging or page tables. All right, so this all we have studied. Okay, any question up to this point? We are trying to look at very gross and top level, right? I mean, not going into too much detail, but basic concepts we are touching now upon. Okay, all right. Then we have studied the concept process, which by now you know it very well. Any program that's in it has to be compiled, has to become executable file and brought into main memory for execution. Then now we have seen the structure like stack, heap, etc. Okay, so we have then it forms a process. Okay, and then a process of course will have code part, then data, it's like mainly static data in the files, and then state of a process at any point in time is determined by its registers and the value of and the stack, etc., right? Okay, so if let's assume the process is in execution and is moved out to run any other process in CPU, then that state of the process to be stored, and that state is determined largely by this thing, the value of register, the stack, and the various register like program counter, etc. Of course the stack is there, and stack pointer also has got to be there, and set of open files, etc. We have also studied the concept of thread, which is a lightweight process. So essentially in that the common part is this code remains the same. Actually it's see it's basically same code is executed, but control of that execution, a point of that execution varies from thread to thread. Okay, so here something that's common is code, data, and files, and each stack will each thread will have its own registers, stack, and program counter. Okay, so these define the state of the thread at any point in time, but note that code and the files that are open remain the same. Okay, so why do you need threads? It gives us efficiency, right? Thread context switching of threads within a process doesn't require much time. And second reason, main reason is that then many programs or tasks that we are doing can be done more efficiently using threads. And of course, threads become individual unit of what do you call that, scheduling, and then threads can also be scheduled onto multiple cores of a processor or multiple processors. Okay, all right. Okay. We have already discussed these points. The thread within a process share heap, global data, and libraries, and each thread has its own PC, stack, and register values. And then there can be multiple threads in a process, within a process, right? So we can have multiple threads, and each thread will have its own stack. When we say stack, it means that stack will contain variables and other things, right? And each stack may have multiple frames. Okay, if a thread is calling some other function, and that function is calling third function, or if there is a recursion, then there of course there will be multiple frames. All right. Okay. Any question? All right. Then we have seen that very simple concept that if there is a single processor, then OS has to be come into the play. Otherwise, user program will hog all the bandwidth or all the resources, right? Okay, second requirement is that user program also need to take help of OS for doing IO and many other activities. Okay, so it means that the system has to be in one of the two states, okay, which we call it user mode or kernel mode. Okay, kernel mode is a privileged mode. It may have some specific instructions for execution. Okay, may have, which if user process wants to use, then immediately system will move into kernel state. Okay, we have seen that user mode to kernel mode can happen by various methods, and similarly kernel mode to user mode, like syscall is one such thing. The return from return could also be there from kernel mode to user mode, and we have studied all these ways in which this transition can happen between user mode and kernel mode. Okay. All right. Okay, then we have seen concept of multi-programming, which is nothing but having multiple process in main memory which are in execution. Okay, and then OS provides CPU to these processes in some order, which is governed by scheduling algorithm, right? So each process each process runs on CPU for some time, and then other process starts running. In that case, first process is moved out. That we call as context switching. Okay, and this concept you have seen, the concept of process abstraction. Okay, we have also seen how process is actually created. We have looked at this process. For example, load code, static data from disk, make it executable, create initialize runtime stack, create heap, etc. Right? So these concepts we have studied. Then we also looked at life cycle of process. The process starts from initial when process started or a new process created, then it comes to ready state. It means that it's ready to execute. Okay, and then it starts running whenever scheduler schedules it, and then it may go to if it does IO, then it goes to waiting state. Otherwise, OS or hardware interrupts it, then OS comes into play, right? So there is interrupt, the process is moved out, OS starts running, and OS may schedule same process, another process, right? So all right, and finally process may want to do IO, come to waiting state, and then from it, once IO is complete, it goes again to ready state, and then it starts running, and sometime or other it gets completed and gets terminated. Okay, so we have looked at all these states. All right, same similar life cycle exists for each thread. It's exactly similar. Okay, and transitions are also very similar. Then we have seen that process state has to be stored, because once process moves out of processor, and it means that all the information must be saved somewhere such that it can be restarted from that point onwards. And we have seen there's something called PCB. Now different OS call this structure by different names. Okay, PCB is generally old terminology. Linux uses different name. Okay, and then we have seen what all is saved in PCB. Okay. All right. This same thing that we have discussed earlier. Okay. Basically, is a thread control block, which will have all these things that we have mentioned here for process. Similarly, for thread, it will have some of those things, right? Mainly stack pointer, registers, PC, etc., and thread metadata. Okay. Then we have seen that everything looks good, but user program, if wants to do IO or some other activities with the help of OS, then it cannot directly go and execute, or directly run printer, for example, or cannot directly go to disk and read the blocks from there. So there is a concept of system calls. So OS specifies certain APIs, okay, or interfaces, and that are given as a system call. So using this system calls, user process can interact with OS for different activities, right? So we have system call interface here. Okay. Okay. So apps can use this directly, or apps can also use OS library. Okay, and OS library in turn can use system calls. And reason for using OS library is because of simplicity, because OS library give us simpler interface, okay, and can do a lot of things for efficiency. You know, for example, you know, it can have a buffer for, you know, storage of temporary data, etc. Right? Okay. All right. Okay, and we have so this. Okay, so this library, it's not necessary for user process to use library. It can directly use system calls. That concept we have studied. Okay, and this flow we have studied wherein application program uses a library, and then library in turn uses syscall, and then syscall when it goes, syscall is used, then OS comes into play, and then syscall handler, which is part of OS, executes the system call. Okay, it could be like reading a block or whatever. Okay, then we have gone into details of process and threads, and we have seen how a process, because when a system boots up, OS boots up, there is just one process, then other processes are to be forked from there, right? And we have seen a concept of fork system call wherein a replica of the process is created. And then we have looked at exec system call, because there is not much use if the same process is created as a child process, right? Then the child has to behave differently, then it has to inherit some code from somewhere. Okay, and using exe system call, the child process can take code from, you know, some code, and then starts running, right? So we have seen studied exec system call. Then we have seen a parent can wait for child to die, okay, or child to complete, and then we have seen this flow. The parent waits until child completes and exit, and then parent, once child completes, then parent can exit. Okay, and using this abstraction or method, we can create different kind of programs. Okay? Then we have seen how IPC, because the processes by itself, multiple processes in isolation means very little, so process need to communicate with each other. And we have seen the following methods like pipe, we have looked at FIFO, we have looked at of course socket at the end we have seen, and then shared memory. Okay, similarly the process needs to be synchronized. Okay, you know, such that there is a critical section in which only one process can use at a time, and then we have, so processes need to synchronize at certain point in time. Okay, and we have seen a lot of examples around it, and then we have seen the methods. We started with conditional variable, then we have looked at mutex, and then semaphore. Okay, any question up to this point?
No, sir.
Okay, good. Okay, so now we know that there are multiple processes, multiple threads in a system, because every system, even simple laptop that we have, will have hundreds of processes running at a time. Okay, and assuming that there is only one CPU or one core, then only one process can run on the core at a time, and OS of course is also a process. Okay, so something must determine in what order this process can run. Okay, or how much time each process will have to execute. And it also has to define such that process can be asked to leave CPU, or it has to be context switched. Okay, so scheduling gives us that algorithm. Okay, so first simple algorithm that we have seen is first come first serve. Okay, and this is how we use, in shopping malls or airport and so on, right? And there is no priority here, right? The one is who comes early will get served first, but this also has, this normally in life we use it, or a variation of this. Okay, and so it's a very popular method, but that takes away a very important concept of having a jobs having priority. Okay, so there is no concept of priority here. Okay, and if there is a job that is big in size, and then it can block very small size jobs, that are that are behind it, right? It's called head of line blocking, or convoy effect, or something like that. Okay, and then something that we also use often is the round robin method, right? So now round robin method uses preemption. So concept of preemption is comes here, while earlier was is a run until completion. So here each person or each job is given some time. After that, the job is preempted or context switched, and the other next job comes into picture, and then third job comes into picture, and fourth, and so on. The order here, note that the order here is fixed. Okay, and then there is a round robin, means that the first job again given time slice up once all other jobs are covered. Okay, all right. So this is very simple method, but it has its own issues. Okay, and then in order to improve on that and bring in the concept of priority, for example, round robin didn't have concept of priority. So in order to bring in concept priority, we had multi-level priorities queue scheduling. Sorry, and we have seen that we can create queues based on the priority. For example, priority 3 is the highest. So first all these jobs will be, once all these jobs completes, then control comes to, or the CPU is given to the jobs in the next queue, and so on and so forth, right? Okay, now it also had some problem, because there can be starvation. If there is a continuous flow of jobs at highest level priority, then lower level priority jobs will never get time to execute, right? So starvation is a problem. Also there was a problem of priority inversion. And then we have seen concept of lottery. This very nice interesting way that jobs having more importance, or the job that needs to be finished first is given more tickets, and then one ticket is drawn at random, and with good probability that job that has large number of tickets will get more chance to execute, right? So this interesting way, and then we have seen very interesting algorithm that is used today is called CFS. It's used in Linux, and there is the concept of no time slice, and we create epoch, and within that there is also concept of what do you call that, wow, nice value. And nice, and based on that, if you want to be nice, then you say that I don't need CPU for whatever is 1 by nth time slot, I will use less. And based on that, every job gets executed in epoch, and then once it's complete, then based on the jobs again, this epoch is created and same process repeats. Okay, so this is very interesting way of giving doing scheduling. Okay, and there are many other variations of CFS. Of course, we have not covered everything, but the algorithm that we have covered gives us fairly good idea about what scheduling is. And then we have seen in normal life also deadlocks can happen when all processes that are in execution come to standstill. because processes want resources which are kept by other processes. Okay, and then we have seen there are 4 necessary conditions like bounded resources. Okay, if number of resources are all limited, okay, no preemption, it means a process, a resource that in use cannot be taken away forcefully. Wait while holding, it means resource a process holding will continue to hold, and for more resources. Okay, so thread holds one resource while waiting for another, and fourth is circular waiting. Okay, in order to come out of or break deadlock, we have to at least do away with one of these conditions. Then we have looked at the Banker's algorithm, which is based on the worst case resource needs, and it allocates resources to process only if it knows that it can satisfy the demand of all. Okay, in some sequence. Okay. So we have looked in detail about it, the concept of safe state and non-safe state, etc. And we looked at some examples. And then we have studied file system. Okay, we have looked at the concept of stream or file pointer, file descriptor. Okay, is concept of stream, then file descriptor. And then of course we have studied system calls, and then we have also seen how all these are implemented. Okay, we have also studied then how file systems are implemented. We have looked at structure of disk, which has number of tracks, and within track there are sectors. And then to do away with all these details of disk, because there can be disks of various types, the OS defines that now disk is to be viewed in terms of number of blocks. So it does all IO with disk in terms of blocks. So it knows what is starting block number, what is ending block number, and block becomes then unit of transfer. Okay. Similarly, we have seen the concept of SSD, and we have seen the limitations of SSD, advantage of SSD, that we can, in order to write something, we have, and that if it's available, then page can be written, otherwise whole block has to be erased. Okay, so those are limitations, but we have seen that SSD is becoming very popular, and after a few years, maybe 3 or 4 years, SSD, all of us will have only SSD in our systems. Okay, because the cost of SSD will come almost at the same level of hard disk drive. But hard disk drive has been in existence for many decades, and is still a great technology. Okay, we have also seen the concept of how from a process that is using a file descriptor, okay, we can access the content. Say for example, using file descriptor, we want to just read a byte or an integer, then we have to, whenever a file is opened, a process may open a file multiple times. Each opening of file gives a descriptor which defines the position of the file pointer within the file, assuming that file is a linear sequence of bytes. Okay, and then we have concept of system-wide file tables, which will have, for each instance of file opening, okay, it will have some data. Okay, and then we have concept of system-wide inode table, and inode does not tell you the position of the file, for like file pointer, but tells you everything, where the file is stored and size, and who is the owner, and what is the access control mechanism, who can read and write, and etc. All these permissions are also mentioned here. Okay, and of course we have seen that how inode is actually structured. There are data blocks which can be accessed direct, and there indirect data blocks and double indirect data blocks. So here, for example, a file size can also reach kind of terabyte. using this method. But this is kind of optimal mechanism because most of the files are generally smaller in sizes. Okay. So that let me just come to the last one. Is that all? Okay. All right. So apart from this, we have also covered a little bit about data center and cloud. Okay, and this is becoming, cloud and data center is becoming an architecture by itself, right? Because most of us don't use all the, if you're doing a task, right? Say 30 years back, in the computer, we are doing all the tasks. There was hardly any load distribution. Right now, our device is just starting an application, but most of the competition may happen at data center on various machines, and information is collected and given to us, which our machine can process and present. Okay. All right. So data centers and the cloud are becoming very important, right? And now the data center design is to be done in such a way that a lot of optimizations are possible. For example, communication delay has to be controlled, unlike local area networks where there is hardly any hierarchy, right? In your department, for example, the things keep changing depending on the requirements, right? But in data center structure, local area network structure, etc., is all fixed. Okay, it's all machines of same type. Okay, and then so all these need to be optimized. Okay, it's interesting to know that a lot of inter-processor communication happens over layer 2, or sometimes happen layer 2 over layer 3. Okay, just for optimization reasons. Okay, and then all these data centers give us an interface which we call as the cloud interface. Okay, so cloud interface is nothing but an abstraction of what services are provided by data center. Okay, data center is nothing but say 10,000 or 100,000 of computer connected in a very specific way. And then of course a lot of things can happen, like it can run application like Gmail or Amazon.com, or for example Facebook, Twitter, etc. Or it can give us resources. For example, from Amazon cloud we can get either application or software as a service. We don't care about how it's implemented, but my application, for example, my billing applications is just implemented there, and then it executes. Okay, it doesn't matter to me how many nodes it uses or how much memory it uses and so on. Is left to the service provider, that data center service provider. Okay, all I need to calculate is what is my SLA, what is response time for my application, how many users can use it, and so on. Okay, and second way of hiring this is by hiring a platform. Okay, for example, Linux platform, or some database platform, wherein that platform on which I can run my own application is also possible. And third is, of course, which is called first is called software as a service, then infrastructure as a service. And what is the third one? What is the second one? Anybody? Software as a service, platform as a service, and infrastructure as a service, right? So the infrastructure as a service we get, we generally ask for in terms of computing power, number of virtual VMs, virtual machines, then how much SSD and how much hard disk and so on. So basically we can take very raw computing as infrastructure as a service. While platform as a service is higher level abstraction that we get. And then application as service, we worry only about applications execution SLAs. Okay, so that's all we have covered in the course. I hope you learned something. Okay. All right. All right.